So in 10.3, we'll be taking a look at hypothesis tests for the population mean. The process will be very similar to the one we were using for population proportions. There'll be a couple requirements. The first two are ones that we don't worry about. They're just kind of given in each problem. The next one is one we're familiar with, that the check or the requirement is that either the population was known to be normal or the sample size is at least 30. That gives us that we've got a approximately bell-shaped curve, except for the fact that we will not be having the value of the population standard deviation, meaning we'll have to use a sample standard deviation, and that determines that we actually won't be able to use the official normal calculations from our calculator. We'll be actually dealing with that student t distribution again, so the t-chart, with the n-1 for the degrees of freedom. That's all going to be similar to what we did with the confidence intervals back in Chapter 9. But as far as the process of hypothesis test, it is almost identical. The idea that we start off with the two hypotheses, and same as with the proportions, either there's the not equal to, the less than, or the greater than, giving us one of our tests. We get a test statistic formula that looks very similar to what we've seen before for the t-score formula using x bar, and now mu naught, mu sub 0 is again that currently believed to be true value. Other than that, that's the same t-score formula we've seen in the past. The critical value, this part of the process is the part where we have to use the t-chart, the t-distribution chart, using alpha and the type of test to make sure we understand exactly which column we're in, along with obviously the degrees of freedom needed to look up at the chart. And once we do that, steps 4 and 5, the decision and conclusion, are exactly the same wording, same approach as they were in the last section. So taking a look at an example here. So we assume the resting metabolic rate, RMR, of healthy males in complete silence is 5,710 kilojoules per day. Researchers measured the RMR of 41 healthy males who were listening to calm classical music, and found their RMR to be 5508.07, with a standard deviation of 992.05. At alpha of 0.05 level of significance, is there evidence to conclude that the mean RMR of males listening to calm classical music is different than 5710 kilojoules per day? So throughout there, we see a couple mentions of the word mean, right? So it's kind of obvious that we're testing the mean. We also don't see that our population was normally distributed. However, we do see our population size of 41, and that's at least 30. So that's all we needed to see there to know that we can use our normal approximation or our t-chart, t-distribution approximation. So for our null and alternative hypotheses, starting there. Well, like we said, we know we're doing a test about the mean. We are saying that it was originally believed to be 5710, and we're asking if it is now different. Different meaning not equal to. So not equal to the 5710. Okay, from there, after the hypotheses, we move on to the test statistic. So that comes from our formula of x bar minus mu naught over s over root n. So the sample mean that we got from our sample was the 5508.07. The mu naught again is the currently believed to be true 5710. Divide that by the standard deviation of 992.05, square root of our sample size, which was 41. So let's see what we get there. Getting negative 1.303 for our z naught, or again, our test statistic. Now with this approach, we're going to use a classical approach just because the p-value approach is a little more convoluted, and with the chart, the t-chart, it can be a little confusing if we use the other approach. So we'll stick with a classical approach here, meaning as we go to find our critical value, we have the not equals. Not equals means we're dealing with a two-tailed test. To draw that picture, knowing that alpha is 0.05, we know we need half of alpha. We need each of these tails to have an area of 0.025 in them. And so that helps us to know which column of the chart we're going to be looking up. Also, to point out, we do need to know our degrees of freedom, which is n minus 1. So our sample size was 41. So our degrees of freedom will be 40. And so we can use our chart with the area to the right tail. So technically we're looking at this tail, although we know this is symmetric. Area in the right tail of 0.025 and a degree of freedom of 40, way down here. So following the 0.025 column down, 40 across, getting 2.021. So from our chart, we're finding out that this value is 2.021, which tells us that this is just a negative 2.021. So either of those, both of those, technically, those are our z sub alpha over 2's. Those are our critical values. From there, we can make a decision where, imagining that picture with those boundaries, if those boundaries are at negative 2.021 and 2.021, our test statistic of negative 3.03 is not further than that, right? Not lower, not smaller than negative 2. So somewhere over there is negative 1.303, and that does not fall into the critical regions, or again, the rejection regions. So we're going to not reject the null. And then based on that decision, we will make our conclusion, starting with, at a level of significance of 0.05, but if we're not rejecting the null, we say there is not sufficient evidence to support the claim that, and now we just put that alternative back into words. Our claim was that the population mean RMR would be less than the 5710 when listening to calm classical music. So that the population mean RMR of healthy males would be different, actually, not less than, would be different than 5710 kilojoules per day when listening to calm classical music.